Hello everyone and welcome to a new episode of Golang Cafe, and today we are going to talk about reflection in Go. Reflection may seem one of the most obscure techniques or libraries you have seen so far in the Go programming language or Go standard library. But I can assure you that reflection is not something new specifically to Go, but it's something that's been around already in other programming languages if you have looked or worked with Java, PHP, JavaScript, for example. Reflection is a form of metaprogramming. I will link to the description an article to metaprogramming below if you want to further read about it. Although reflection in a sentence is effectively the ability of a program to introspect and inspect its own structure, and specifically to go to inspect the types of the data and variables of itself. It's a form of metaprogramming, so the metaprogramming itself is the ability of a program to manipulate, read, analyze other programs, or manipulate, read, analyze itself, and also change its behavior at runtime. So it's a very interesting concept if you think about it, because it's very powerful. And today we are going to see where the reflection is used, especially also in the Go standard library. There's a lot of places where the reflection is used and why it's useful. Let's crack on with one of the examples that I have put together. Before we start with the reflection specifically, what I wanted to go through is just a little bit of theory on how the programs are structured in the Go runtime and how they are structured before the program is run. So when the Go program is parsed, all the programs itself in general, not specifically to Go, but all the you have to think of all the programs in general. They're organized into two different structures, two different set of things. The first thing is data, and the second thing is instructions. Okay, so any program that you can think of is composed of data and instructions. Reflection allows us to, at least what we're going to do today, we are gonna see how reflection can allow us to inspect the data that our program uses. So the data that our program uses in this case is a set of variables. It's the variable x. There's a type float 64. A variable u. There's a type user and a value bob10, a composite value. And the value here is 3.14. So the data of our program here is just two variables. So the instructions of our program here are just to print instruction, print x and print u. So whenever the Go program is parsed by the compiler, what happens is that it's going to be organized in memory in such a way that the data is structured within the types. And then you're gonna have the values, you're gonna have the types, you're gonna have the identifiers, and then at some point you're gonna have an instruction list. And so the program starts from 0 and says, okay, what's the next instruction? The next instruction is print the variable with identifier x. So it says, okay, I need to print the variable identifier x, and I go back into the data table, look up x, check the type, check the value, and says, okay, I need to print the type float64. Print knows how to print types with float64. It takes the value 3.14 and prints out to the standard output. Same goes for you, the type named you. So this is what happens more or less when you run a program. The reflection allows us to see what the types are and what the values are of our data. We're not gonna see now, the instruction bits. So the instruction, you can ignore it for now. But you know that each program is composed by data and instructions. The reflection allows us to introspect the data of our program. Okay, using the using standardized types. You have some types that you're gonna use, and those types are kind of a box inside which you can put any type of data. Okay. So you have any type of data, and you have a box where you can put all this data inside. how the data is called in Go, how those variables are called in Go. Those is like a table of something, right? So a table of something, how do we call this something? A table of something is a table of interface values. So we call this, our variables in general in Go, we say that are interface values. Interface values, our table specifically is composed of a tuple of, we also have the identifier, but more specifically for the reflection, something that is very relevant to the reflection is that interface values are composed of two objects, are composed of value and type. So we know that this table has two columns, value and type. We know that X contains a value 3.4 and a type float 64. U contains a value Bob 10 and a type user. So this is what the table is going to look like. If we want to modify the table to again to make it look like what the value is, we can just do that. So we can just say, okay, this is our value. This is our value. This is our type user, and then we have the value 3.14 and the type float 64. This is exactly the same table we have seen before, the data table. This is what gets executed. This is the data that is inside our program, and then there are the instructions, and this is the data that we have. And in Go, this is called interface value. So this is an interface value, use an interface value. Each variable is an interface value. And each variable in memory is represented, inside the Go runtime is represented with as a tuple, with value and a type. Okay. Now, with reflection, we have a general purpose object that we can use to store any type of interface value, regardless of the type, because we know that we have a non-finite number of types, because we can define any type we want. So if we say type user, then we can say, type big number, and that's an integer. So we know that we can define any type alias, and this big number, if we define a variable, then it's going to go into an interface value, and the type is going to be big number, and the value is going to be the value we assign to it. So the types are not something that we can know in advance, are something that the program cannot, that Golang, the Go runtime cannot know in advance, and the reflection cannot know in advance. So what we do, we have some general purpose objects that contain for us those value and type, and those are coming from the reflection reflect package. So those are called reflect value and reflect type. And those are called reflection objects. Those are like if you go a layer up in the abstraction layer. So reflection objects are effectively an abstract representation and a wrapper on top of any possible type you can think of, any possible variable you can think of. But instead of having any possible type like user, big number, integer, float 64, you name it, you just have reflect.type. And inside you will have a value with the type itself. Same goes with reflect.value. The first law of reflection that you see in the website, in the Go blog, is that you can go from, the first law, you can go from interface value to reflection object. How do you do that? So reflection object is reflect value of our value x, for example. And remember that we always have a tuple of objects. So we have now got the reflection object for the value. We also need to get the reflection object for the type. Well, you can. It's not that each time you have the object for the value, you also need for the type, but it's for illustration purposes. That this is the case. You always have a type when you have a value. So if you have a value, you also have a type. Reflect, and you can use the type of x. So this is like a box, a wrapper on top of your basic type. And I like to think of reflection as if you are working with containers, like if you are actual shipping containers on a ship, and you have a general purpose behavior and a composable object and a predefined set of behaviors that you have with reflection objects, and then inside those objects you can have anything. You don't know what you're gonna have inside, but you know that you have lots of stuff. You know that you're gonna have lots of types. You know you're gonna have different values and different types. But regardless of what is inside, you can still work with the higher level abstractions, which are reflect.value and reflect.type, which allows you to introspect the values of your variables. So the first law of reflection tells you that you can go from interface values, which are our variable, into reflection objects, which are always reflect.value and reflect.type. This is the first law of reflection. And let's see now what those reflection objects, what we can do with those reflection objects. Let's just quickly printf. So reflection object value for x. So the reflection object, how is this represented? And then I also want to see not only this, ref obj val string. You have a method that allows you to see the reflection object value string and the reflection object type, because we said that each variable is always a tuple, so you always have a value and a type, both with the interface values and with the reflection objects. So here is a reflection object type string that should do the job. Go run reflect. So we first printed the actual values 3.4, 3.14 and Bob 10. Then for the initial one, the float64, with the reflection object value for x is float64 value. A reflection object type for x is float64. So the value doesn't show 3.14, but this will contain 3.14. Will contains the fact that this is a float64 variable, and it shows it in a way that it's clear that this is a value of type 464, and this just contains float64. It says I know that this is a float64, I don't know what value it is, I know that it's a float64, and it says I know what the value is, and I also know that the value is a float64. So it's kind of it knows the type of this variable, and those are the two. Is the tuple, the value and the type. And you can check more information about the value directly into the documentation of the reflect.value interface.go value. So here you have some methods that you can use. Obviously not all the methods apply to any type that this value is wrapping, is boxing, but you can see that most of them, some of them will apply, so string will apply. In our case, if we want to see the actual value, what are we gonna do? We are going to go back and see what's the float value. Can we see the float value here? Let's see the float. Yes, we can do the float value. You can call float, and this will return a float value. So we'll reflect. If we want to see the float value of a reflection object, font printf reflection object value for float x, float64x, is reflection object value dot float. As you can see here, it is showing us the actual contents. So the reflection.value, the reflect.value, it is kind of a polymorphic structure that will be containing any type of information about any type of variable, because inside the reflect.value you can put a float, you can put an int, you can put a string, a boolean, a struct, any type you want. And at certain point you can also retrieve the value back. So when you retrieve the value back, you can use the appropriate method based on what you put back in. So, and you know what you put back in because you have the type. You know the type here. You can retrieve back the type from the interface value. So, and there is some equivalence here, which is like reflection object type is also equal to reflection object value dot type. So if you do value of x, you get a value reflection object value. This one is a type method which returns the same as the type of x, which is float64. Reflection object type is float64. Reflection object type is float64 is the same. This is the same value because it represents the same type. And those are two equivalent ways of retrieving the value. So the second law of reflection, we already saw it. The second law, you can go from reflection object to interface value. So you can go from interface value to reflection object to interface value. And the third law is that we're gonna see the third law in a moment. And now what we're gonna do, we just read the value from the reflection object. We transformed our value into reflection object. We read the value back from our reflection object, and we want to try change the value of our reflection object directly. How do we do that? There is a method called set that we can call, but before you call the method set, you need to call the method canSet. So canSet new value for reflection object. And how do we do that? We can do ref object val canSet, and I'm gonna explain you in a second what this means. If you go into go.doc_reflect.value, which is our box, our container of things, if you go into canSet, you will see that the canSet reports whether the value of v can be changed. So if we now go and run it, we see that it says that it cannot be changed. So we see why it cannot be changed. It cannot be changed because what we are passing inside here, it's just a copy of x. And this is true not just for reflection, this is true for any time you pass a variable into a function. When you pass a variable into a function, you're just passing a copy of the variable, you're not passing the address of that variable. So what we need to do, we need to change that to be a pointer to x. So we pass the address, a pointer to x, and this now becomes object val ptr. So it's a pointer, is a reflection object again, but this time the type is not going to be float64. The type is going to be, we can actually see it without changing anything here. You're gonna see the type. So, and the type is pointer to float64 value, and obviously we also need to change. Here to keep it consistent. So, need to pass the address of type of. So the the reflection object value for x is a pointer to float64. Reflection object type is a pointer to float64. And then it says colon reflect of value of float on ptr value, because float can only be called on the actual value, not on a pointer to the value. So we need to dereference the value if you want to get the value back. How do we dereference with using the reflection? So we just need to go back into our reflection example, and what we are gonna do, we are going to basically refresh how the pointer operations work with Go, and we have seen in one of the previous episodes, which I will also link in the description below, where you have a variable x, for example, in this case 3.14, and you want to get a pointer of that. You can just do, as we did, we can just do %x. If you want to get back the value of x, how do you do that? Use the dereference operator, which is a *x. So we have seen how do we get the pointer value with the reflection type of and value of, but how do we get back the value? still working with reflection objects. There is a specific function that we can use, and this function is called lm, which we're gonna call now. We're gonna see now. So we're just going to rename this to reflection object value pointer. So it's clear that this is a pointer. It's not a value. It's a pointer. So we cannot call the pointer anymore on the float. Dereference the pointer to its actual value, and ref object value. Now we can declare it again, and we can do reflection object value ptr lm, and this is the same as doing the reference operation. The lm goes into the pointer and says go take the variable at this memory address to which you're pointing to, and that will return a reflection object representing that variable, which in our case is the x. So the actual value here then is going to be a float, and now we will see that things will start to make sense. So now reflection object value for x is a pointer to float64, the type is a pointer to float64, we did the reference with lm, reflection object value for float64 is 3.14, can set new value for reflection object, it says true, so now we should be able to set it, and you will see now why. Golang reflect.value.lm returns the value that the interface v contains or that the pointer v points to. So in our case the pointer v points to. Our value is a pointer, the pointer points to some value which is our original 3.4 float64 value, and we get it back. And still, this still returns a value, it doesn't return a float64. So if you still want to do operations, or we want to retrieve the float64, you need to call it back on the reflection object. Now if we want to set it, we can just call reflect.value.set, you set the value. So the value here is going to be, if you want to change the value using reflection instead of setting it directly, we are going to do something like the object value that we retrieved from our pointer. So it uses the reflection to go into the pointer goes into the variable that it points to, and then we can call it set, and then we can set a new value. And then instead of 3.14 we say 4.25, and then we do fampt printf reflection updated x using pointer and reflection object. Now value is equal to, let's see, the value of x. So now the value is updated. We have seen we haven't actually touched the x, we haven't changed x, we've just taken the address of x, we have created a reflection object for that pointer, we have dereferenced the pointer, so we get the actual reflection object for x, the actual x that we want to modify. We check if we can modify that. It's true, we can modify that. We updated the value, and now the value is 4.25. So this is what you can do with reflection. And the third law of reflection is exactly that. The third law of reflection is that you can when you try to change when modifying reflection objects, not all reflection objects can be settable. Modifying reflection objects, not all of them can be settable. So you always need to call can set before you call set. So this is very important, because with reflection what happens is that you don't have any more the constraint of the compiler that checks for errors. So you're gonna have a lot of runtime errors if you don't do things properly. Because it's like if you have a very loose typing and you are trying to set any value and you're not caring about any type of constraint on your program. You're just trying to modify the structure of the program but without the compiler telling you where you're doing things wrong, because this is like an abstract way of modifying the data. So I know that is a lot of things, and I think the gist of that is that you will have to bear in mind that each interface value, which is the variables, can be boxed into a general purpose type tuple, which has reflect.value, reflect.type. And with that you can inspect the type, and you can inspect the value contents of your variable, and you can also change the contents of your variable. We said that you have a tuple with value and type, and I just wanted to also do the same thing with our user object. So you can see one last property, and then we're gonna go through one last example, which is gonna be more fun, which is the JSON encoding example. So our last property, our last exercise is going to be okay, just going to copy this, and wanted to run all the reflection object value and type. And this time we are not going to use the pointer. I don't want to change the value. I just want to see what it looks like. Main.user. This is showing as 464 probably because there is some issue with the value of yeah, because we have to update the variable here. So as expected, what we get here is our type alias, because our defined type is main.user as a type, and a value is value of main.user. There is still one thing that you need to be aware of when working with reflect, and it's the kind. Kind represents the specific kind of type that a type represents. So here you have a general, you have a type that's been defined by you, but the kind it's in itself, it's one of the finite set of types that a variable can be. So in our case, the type is main.user, but the kind is a struct. So it's the kind of type, effectively. It can be a struct, it can be a string, a slice, a PTR. And so you have a finite set of kinds that your variable can be. And this is something that you can actually check when working with the type or the value itself. And you can do that. You can do object kind, and you can get this either from the type or for the value. I think it's the same, if I'm not wrong. Go run reflect. So the type for u is main.user, the object kind is a struct. In this case, we're just going to do it as well for the uppercase there, because it's going to be interesting what's going to show. You're going to see that should show that this is a PTR. Kind for x is PTR, should be PTR. Type. It's PTR, exactly, it's pointer. Because it's a pointer to something, but in effect, the kind of type is a pointer. Here is a main.user, but the kind of type is a struct. So you got the main difference between the kind and the type. So now what we're going to do, we're going to implement a quick JSON encoding function using reflection, and this is very similar to how the JSON encoding is implemented in the Go standard library. Obviously, our implementation is going to be much simpler, much simpler than the one that you have in the Go standard library, and that's because there is a lot of code that you have to write if you want to manage all the types that you want to deal with. But still, our objective is going to be able to write a function that takes an empty interface, and it doesn't know the structure of the struct that you're going to pass in. It just knows that the input is going to be any struct, so we support as an input just a struct, and as a types we're going to support a string and an integer. So we know that these are the types that we're going to work with. And you could extend that to be something else, but what we're going to do is just that we're going to work with the string and an integer. We also need to define tags, name and age. If you want to, those tags are going to be used as an output to your JSON. So our output should be something like name Bob and age 10. And using reflection, how do we do that? So with reflection you can inspect the values of your variables, so not only the type and the value, you can also inspect in the struct, you can also inspect the fields, the number of fields you have, you can inspect the types you have, you can inspect the name of the tags you have. So now it becomes to make a lot of sense why you can use reflection with that. So one of the first thing now is we're gonna get reflection object value using reflection reflect.value of, as we've done before. And then from reflection object we want to check the kind. The reflection object value is reflection object value dot kind. If this is not a struct, then what we're going to do, we're just going to return, I just need to define a buffer here if you want to. If we want then later on to return our value and an error. So our error says that value of kind, the kind you passed is not supported. So we're only supporting structs, and the kind is ref object val ref object val dot kind. This is what is not supported. Then we know that we need to go through our struct. How do we go through our struct? There is a method in the reflect that you can inspect all of this and you can see. The method is called number fields. Num field returns the number of fields in the struct. It panics if v.kinds is not struct. So you can get the number of fields in the struct, and then you can also access one of the fields using field, and that returns a reflection object for that field itself. So that comes in handy if you want to iterate through the struct. And so we do that. We have our iterator, and then we go through that and we do we know our reflection object value, number of fields that we have, and we go through them. So now what happens is that we want to check the type. So we are now going to name, into age. That's our for loop. It's going to just be 2 elements. So now for our type, what we want to do, we want to know what the kind of this type is. Okay. So if we want to know the type of this kind, we're just going to use the ref object val.field. So struct field, again this is struct field, reflection object is reflection object value field at position I. So this now is a representation for name, string name, representation for age in 64 age. And so now we need to check the kind. So we do struct field reflection object, and we get the kind, and we know that we support string, so reflect.string we support, and we also support the int64. That's why I put the int64, because int is an alias for int32. So now I just put int64. Obviously you will have to do, in the actual JSON encoder, in the actual standard library, you will see int64, int32, and all of that. Just int64 to be clear and concise that this specific type is supported, but you can extend that to be any type, any integer type. And then we say that otherwise, at the moment, it's not implemented because we're just doing 2 for now. But you got the gist that then after that you can effectively you can extend your logic to work with other example as well. So we are saying that struct field with name this name and kind this kind is not supported. So how do we get the name of the struct field? Let's see how do we get the name. So if we go into the go.doc reflect, we know that this returns a value. So the struct field is a value. The value doesn't have a name. But we know that if we get the type, if we get reflect.type, we reflect.type, we can do the same thing we have done using the field, and this time you get the type information. So you have to think about what we have done. We have just gone through the name, string, name, age, in64 age, and all of that. But you have to think about the struct field reflection object as being just containing the string and the Bob in 64 and 10, but it doesn't know how the field is named. So we need to get information on the field name and the tag name. And how do we get that? Well, we can use the type reflection object which we have seen before. How do we get the type reflection object? So we need to the type reflection object for our struct, which this define all the type information, type of our struct. Then we go down this here, struct field reflection object type, and we have reflection object type field position I. So now this contains all the type information. This contains the kind and the type information as well, some type information like the kind. It contains mostly the value, but this contains the type information like the tag and the struct name as well, so that's what we need. So struct field reference object type is what we're going to use here as a message. Struct field reference object type dot name and the kind that we have seen already, which is this one, kind. So go.doc reflect struct field, which is what we got. Struct field gives us the name and gives us also the struct tag. So here when we use the name, it's just a property, it's not a function, because it's a struct, a simple struct. And so we know the kind, we know the type, so the string, or in 64 we also know the name. So now what we need to do, we need to basically build name Bob or age 10. We need to build this tuple of values. How do we do that? So this is a kind of key values pairs, right? So I call this pairs, is a string slice, and in case it's a string, this is going to be, first we need to get the string value. The string value is going to be from our struct field reflection object. We use the interface method, or we could use the string method, which gives us the same thing. So interface method, we're going to see now go.doc reflect value dot interface, which I've seen before already, to get back. This is the second law of reflection. The second law of reflection says you can go from reflection object to interface value. So this is reflection object, this is interface. It gives the current values as an empty interface, so we just have to cast it to string. Or we can just use a string, which calls internally interface and cast it to string for us, so it's the same thing. We're just gonna use interface just to, illustrate the usage of interface. So we know now the string value, which is Bob in our case, okay? So we have our struct field reflection object, we get interface, we get the string, we get the actual value. Now we need to build the key value pair. So we have the value, we need the key, which is the tag, so we need to get name here. How do we get that? We know that we can do that by using the struct field reflection object type. Go.doc reflect, which is struct field, it's a tag So that's the struct tag that we need. So we go back into the struct tag. Now we need to build the key value, build the pair. How do we do that? We just appended pairs. It's just a string. Just append it to our pairs. So our string is our tag here. So it's a string and it's struct field reflection object type dot tag. And then we want it's between double quotes, it's colon, and then you have your string value. You have your string value here, which is string val. And that's it. So you append it to the pairs. So now each time you have a string, it's going to be appended into the pairs. And now we're going to do the same with integer. It's just going to be even simpler. Int val struct field reflection object interface, second lower reflection, go from reflection object to interface value in 64. And then we need to convert it to string, because at the end of the day we are doing a JSON conversion and the final output is going to be a string. And how is this represented? Well, we can still use, here we have our tag, as we have done, struct field, reflection object type, and dot tag, which is a struct type field. Colon, at this time with, here we also need the enclosing double quote, but with the integer we don't need the enclosing double quote. We know that the integer is just then, it's just attached to the colon without double quote in the JSON conversion. So in here we have int val base 10. So this is the int64. This is the tag for our struct, and this is the conversion. We append the pairs. So now that we have effectively we have a pairs that is a string slice, and this contains basically something like this: the tag name. So the tag name is name here. The tag name, and then Bob, and then the second item is going to be tag name, age, and 10. That's how it looks like in our specific example. If you were to pass another struct, it would look different. So now we just need to concatenate all the elements with a comma, and then we basically can finally output our buffer. So we can do write strings.join. We have our pairs, we have pairs, and we have the comma. We have buffer.write string. We have our final and closing bracket, and then we return buffer.bytes, and then we return nil as an error. So this is effectively what's going to happen. So let's see now here. We just need to call now. Our function. So the result and the error, JSON encode. We have a user. If the error is nil, is not nil. What's going to happen is that we just, for now, we just panic. We're gonna see later, and then we print the final string, because otherwise you're gonna see the raw bytes. And also we need a bunch of stuff here as an import. Run reflect.go. Undefined, obviously, error ref, line 51. Error ref, just a typo. Hopefully this time runs. So here, we just have a funny bug. We just missed the initial bracket. We're just gonna add the initial bracket as a starting point, which is buff write string. Oops. And I just wanted to go through one other example where it's like, this is user and this is like city, struct, name, string, and then you have population in 64, and then you have GDP int64, and then you have I don't know, you have mayor. It's mayor string. And I also wanted to go through a scenario where you have a type that is not supported, and type that is not supported. That can be, for example, even a boolean. You know, is city is I don't know, is active city, boolean, active, and mayor, and GDP, population, name, and you also have to then initialize the city here. We're gonna see our error checking, how the error checking will basically work for us. City, and you have a name, you can just use, you know, SF, population is going to be, I don't know, and GDP is going to be some number, mayor is going to be some guy, Mr. John, and active true. City, let's see what happens with reflection. 11, 35, 34, reflection. Okay, so now we have our name Bob H10, it works fine. We have struct field with name active and kind boolean is not supported, because we said that for our example we are not supporting anything else rather than string and integer. So we can remove that, and we're going to see how this plays out. Too many values in city literal. Obviously we need to update the city literal. City doesn't have anymore the boolean value. And you see that now it's working fine, because we know that this is how our structure works. So the JSON encode, we just written a JSON encode that doesn't actually care about the structure of our struct. It just introspects the structure of the types within the struct, but it doesn't care about the specific types or the specific structures, the specific output types. And it's very dynamic. It's a very dynamic structure and very dynamic function. So that's what is being used by the JSON encoder. That's what's being used by also the FUMPT, the format function in the FUMPT, because it receives an empty interface. And if you go inside, you will see that it uses reflection a lot as well. So this is just a simple example of the JSON encoding. Obviously, here we are using the tags improperly, because tags as a convention should be used. As a key pair. So here, for example, that's why you do JSON, right? So the JSON one is going to be implemented in this way. It's going to be implemented in this way, but you can use any key. So it doesn't matter what key or what value you have here. It's just something that then you can use in here. And this is something you can use in the JSON struct. So if you go into Godoc reflect.struct field, you will see that you have struct tag. So the struct tag is a string, is an alias to a string, and you can use the get and lookup. So by convention, tag strings are concatenation of optionally separated key value pairs. So it's a convention. It's not something that you have to absolutely. It's not something that you have any restraints on, but it's a convention, and that's why you always see the tags in that manner. And so if we were to use the tags in that manner, what we have to do, we will have to basically use tag, and then here struct field ref object object type, we get the tag, and the tag has a get method which you can use on the JSON key. And so here it becomes much simpler. It becomes tag, and it becomes tag. So this is effectively what is going to happen. It doesn't change. Okay, it changes the result. It does change the result. Get JSON, and the reason why is because we're not properly formatted, because you need the double quotes. That's how it says in the spec. Otherwise, it's not taking the value, as you can see. And this is very powerful because you can implement JSON, but you can implement anything you want. You can implement any type of custom parser or custom marshaller in this way. For example, a very simple case is like, if I don't think this is very relevant, but if it's something that you want to look into, is like you can have other properties, and based on the properties you can encode with a different field name. So if like here we're doing with the actual field name for a language prefix. So here you could use this kind of structure, and I will show you now how this will play out. En. So here you would have indigo and population is going to be the same, and IT is going to be nome. And then what happens is that in your encoder you can pass the key. So here you can say this is IT, or I don't know, like this is EN, and this is IT. And so what's going to happen is that here tag key string, you can just change it, the tag key that it needs to retrieve, and that it becomes configurable. So here is in English and here is in Italian. So that's you get a lot of flexibility when you work with reflection. You get a lot of flexibility because the program can introspect himself, can see himself, and it can change the structure of the program. It can read the structure of the program. Obviously, now we are not changing the value of the structs. We're just reading the value. But if you're interested, just leave a comments below. We can go through one example where we use reflection to change values at runtime using the reflection objects. Yeah, I think that's everything for today. I hope that you liked the tutorial. You can leave the source code on the description below, so you can go through it. You can go through it on your own time, and I hope you liked the video. Thanks very much. Thank you.